this later on. If you have entered a matrix into Matlab environment, then the next question we want to ask is how to analyze the matrix. How can we find the determinant or other properties of the matrix? Or how can we find the inverse matrix or even generalized inverse of a matrix? And also we need to find the eigenvalues or eigenvectors of the matrix. For the properties of a matrix, we need to analyze those properties, the determinant, the tree, rank, norms, and others. And I think in your linear algebra courses, you might have already met some of the properties. So let's discuss how can we deal with this kind of properties. First, if we need to find the determinant of the matrix, the mathematical form to find a matrix, determinant of a matrix is something like this. It could be quite complicated. We have to find all the possible combinations of the elements of the matrix, and it might be very difficult. And in Matlab, what we need to do is to give a command like this. I will use DET for determinant. And if you have already a matrix, we can find the determinant of the matrix immediately. If A is a double precision matrix, then we use the double precision algorithm to find the determinant. If A is a symbolic variable, we can use DET to find the analytical solution to the determinant of a matrix. And the algorithm they use inside the algorithm is the Gaussian elimination algorithm. And as I have already said, that this function can be used for double precision matrices and symbolic matrices. Let's consider the first example. If we have a matrix like this, and we want to find the determinant of it, what we need to do is first we have to specify the matrix into Matlab environment. Then call the DET function directly. In that case, we can find the determinant of the matrix immediately. So let me demonstrate this part. We have two statements. One is to enter the matrix, the other one is to find the determinant of it. And the determinant of the matrix is 0. And it is a singular matrix. This is the first example. Now let's consider the determinant of a 20 by 20 Hilbert matrix, as I already discussed. The Hilbert matrix is a matrix like this. The general term in the matrix is I plus j minus 1, something like this. And we can use any ILB function to generate a Hilbert matrix. For instance, in this sentence, we can generate 20 by 20 Hilbert matrix. Then we can call the function SYM to convert it into a symbolic matrix. And then we can compare the difference between a symbolic matrix and a double precision matrix. Let's consider this part again. Just to use a shorter term. This is the double precision matrix. It can be found that the element is 1, 0.5, 1/3, 1/4, something like that. But in double precision matrix, for instance, for this term, 0.3. For this term, if you express it in double precision form, you can only get 13 digit numbers. And the other ones are truncated. And in symbolic terms, we use 1/3 directly. There is no approximation to it. So that's the difference between the two kinds of matrices. So we need first to convert it into a symbolic matrix first, and then we can call DET function. And then we can find the determinant of the matrix. Something like this. 1 in the numerator and the denominator is quite long. It has more than 200 digits. So it is the exact value. So this is the determinant of the matrix. We can use DET function directly to find it. And the other property is the trace of a matrix. In some applications, such as robust control, the trace may be used for multivariable systems. So sometimes we need to find the trace of the matrix. So what is the trace of the matrix? The trace of the matrix is defined as the sum of diagonal terms. The mathematical form is something like this. And in Matlab, what we need to do is to execute this command to call the trace function. And this function will calculate the trace of the matrix. Or, from the very basis, you can use this command to extract the diagonal elements of the matrix first, and then take sum of them, so that we can find the trace of the matrix. So the rank of a matrix is also a very important property of the matrix. In mathematics, the rank of a matrix is defined as the maximum number of rows or columns which are independent, linearly independent. And this one seems to be quite abstract. To find the rank of a matrix, if you do not use a computer, it might be very complicated. And if you use a computer, then we can use the rank command to find it. It is quite easy. And this function also applies to numerical and analytical matrices, A. And if you want to use a numerical way to estimate the rank of a matrix, then sometimes one needs to introduce error tolerance. And the function can also be called in this way.
What does the error tolerance do?
Well, in numerical terms, I will explain that by examples later on. Okay. First, we can consider the rank of a matrix. If we have already a matrix like this, how do we find the rank of the matrix? And this is quite straightforward. Command is quite similar to the example in the determinant example. And we can find the rank of the matrix is 3, as we already explained the original matrix, the determinant of it is 0. So the rank of it is 3 for this example. It is not a full rank matrix. So let's consider